In this segment, we will explain how the overall logic is applied. Here, we import all the required Python libraries. Then we define the probabilistic context-free grammar, or PCFG. Our start symbol is S, and it expands into smaller units like A, B, C, and D. Each non-terminal has multiple production rules with probabilities. These probabilities control how keys are shaped. In this cell, we define a helper function called chooseRule. This function takes a list of grammar rules with weights and selects one production according to its probability. This is how we simulate probabilistic grammar behavior. Rules with higher probability are chosen more often. Next, we define expand symbol, the core function that recursively expands non-terminal symbols into terminal characters. It checks, if the symbol is not in the grammar, it must be a terminal, so we return it. Otherwise, we choose a rule using weighted probability. Then we expand each element of that rule. This recursion continues until we have a fully generated random key made entirely of terminal. Here we combine everything into the generate key function. It calls expand S, starting from the start symbol of the grammar, to generate a full random key. The result is a structured but unpredictable key, shaped entirely by our grammar. In this cell, we generate a batch of 2,000 keys so that I can compare my CFG-generated keys with standard random keys. Using Python's secrets module, we generate another 2,000 keys, but this time each key is purely random, with no grammar or structure. Each key is 14 characters long to match the CFG keys. Now we'll evaluate the entropy of keys generated by our grammar versus randomly sampled keys from secrets. Entropy measures how unpredictable a source is, basically how many bits of information it contains. This function computes Shannon entropy for a list of keys. It concatenates all characters, counts how often each character appears, and computes the standard Shannon formula. We compute entropy for two sets. 1. Grammar keys, keys created by our PCFG generator, and 2. Secrets keys, keys of the same length generated uniformly from the combined alphabet using Python's secrets module. This comparison shows how the grammar's structure and probabilities affect unpredictability compared to uniform. We'll get two numbers for each set, entropy per symbol and estimated bits per key. This section demonstrates how a grammar-generated key can be used for real encryption. Here, we import the necessary libraries, base64, hashlib, and fernet from the cryptography module. Then we define a function called derive_fernet_key. This function takes our grammar-based key, hashes it using SHA-256 to create a strong 32-byte value, and then base64 encodes it to make it compatible with the fernet encryption system. After that, we generate a fresh grammar key using our generator. We convert it into a secure fernet key and then create a cipher object from it. Now we take a simple plaintext message and encrypt it with this cipher. Fernet produces a fully secure encrypted token. Finally, we decrypt the token back to the original message, showing that the entire process works end-to-end, using a key produced from our CFG. To understand how random or structured the keys really are, we create a character frequency plot. This gives us two visual distributions. The grammar-based plot shows the structured patterns created by my CFG rules, while the CSPRNG plot shows a much flatter and more uniform distribution. Together, these graphs help illustrate the difference between controlled randomness and true cryptographic randomness. In this section, we generate a full derivation trace from the grammar, showing exactly how the key is constructed step by step. First, we define a function called derive_trace. This function takes a symbol and checks whether it exists in the grammar. If it doesn't, that means it's a terminal symbol, so the function simply returns it. If it is a non-terminal, the function randomly selects one of the grammar rules for that symbol, splits that rule into its individual parts, and then recursively derives each of those parts. This builds up a nested tree-like structure that represents the entire derivation process. Next, we define a helper function called printTree to display this derivation in a readable form. It prints each symbol with indentation to show the hierarchical structure of the derivation. This output shows the full expansion of the grammar. Grammar A represents a fixed structure approach. It always generates 3 segments, and each segment follows the same strict pattern: 1 uppercase letter, 1 lowercase letter, 1 digit, and 1 special symbol. This grammar produces nicely structured keys, but because the pattern never changes, the randomness per symbol is relatively limited. Grammar B, on the other hand, introduces variability. It randomly chooses between 2, 3, or 4 segments, and each segment is between 3 and 5 characters long. The characters inside each segment are selected from any of the 4 character classes. This flexibility increases unpredictability, and as a result, Grammar B achieves higher entropy than Grammar A. Grammar C goes one step further and incorporates probabilistic behavior. There's a 60% chance that a key will have 2 segments, and a 40% chance it will have 3. The structure of each segment is also chosen probabilistically, sometimes following a balanced pattern, and other times using a more irregular mix of characters. This creates a more natural, human-like randomness, while still maintaining strong entropy characteristics. To evaluate these grammars, we generated 500 keys from each one and calculated the average entropy per symbol, the average key length, and the total number of entropy bits per key. Finally, we plotted the entropy values, which clearly shows how Grammar A's strict structure results in lower entropy, while Grammar B and Grammar C offer significantly more randomness due to their variable and probabilistic nature. This comparison demonstrates how the design of a grammar directly influences the security strength of the keys it produces.